Okay, I'm going to be working here on the section 10.3, which is continuity. I have a graph here that we're going to be using for numbers 19 and 20, and then a graph here that we're going to be using for problems 27 and 30. So let's start with problem 19. For 19 part A, we are asked to find the limit as x approaches 1 from the left side, that's what the little negative sign is, of this function f of x. So here's the function, and what we're going to do is we're going to approach 1 from the left. So here is 1, here's an x value of 1, and we're going to walk along our function. As we get closer and closer to 1, our y value is getting closer and closer to, let's see, it looks like about 2. Now, of course, we never get there, but that doesn't matter. The limit is about what happens as we get close. So as we approach an x value of 1, our y value is approaching 2. Okay, for 19b, we are looking at the limit as x approaches 1, this time from the right-hand side. And so we're still going to be looking at that same x value, but this time we're coming in from this side. And we've got to get close to 1, so we're going to go skip over that little dot there, and we're going to keep walking along here, and you can see that our y values are coming down, and they're getting closer and closer to a y value of 1. So our limit from the right is 1. So for part C, it asks, well then, what is the limit as x approaches 1? If you don't put plus or minus, that means you have to check both sides. Now we've already done that, and we notice that we get two different answers. If we get two different answers, then what we'll say is that this limit does not exist. And then the next one, part D, asks, what is f of 1? So this is something we would ask in just a regular old algebra class. If you plug 1 into the function, what do you get? Well, we have a solid dot here. When we plug in 1, it spits out this solid dot, which has a y coordinate of 1, so we get 1. All right, so the last part, part E, says, is this function continuous at x equals 1? So is f continuous, I'm going to put C-O-N-T, continuous at x equals 1, question mark. Well, we have to ask ourselves this question. Is the limit as x approaches 1 of this function equal to the function's value at 1? So in other words, we're asking ourselves, is this limit from both sides equal to the function's value there? Well, we know that the function's value, this side, is 1. So we're asking, is that equal to the limit? But the limit doesn't exist. Therefore, they can't possibly be equal, and therefore it is not continuous. So no. So it is not continuous because the limit does not equal the function's value there. And you can tell in the picture, the reason why it's not continuous at 1 is because we can't draw this without picking up our pencil. We have to pick our pencil up, and that breaks the graph. So we have like a jump in there, which causes us to not be continuous. Okay, now let's move on to the next problem, which is going to be number 20. And we're going to be doing basically the same questions we just had here. 20 A, B, and C. And then 20 D, E, and F. Let me erase this blue here. Same questions. Over here, we're going to change some stuff. Okay, and so what we're going to be asking is we're going to be approaching on number 20, same graph, but we're going to be approaching 2. So we're going to go 2 from the left. We're going to go 2 from the right. We're going to go just 2. And then we're going to ask ourselves, what is f of 2? And then is it continuous at 2? All right, so what is the limit as x approaches 2 from the left? So here's 1, here's 2, all right? So as we approach 2 from the left, we notice that our y values are getting closer to 1. So we get 1 here. If we approach 2 from the right, we're walking along this curve, and we're coming down again to the y value is close. Oh, I said, I think I went to the wrong place. Sorry, let me do that again. Oops. We're approaching 2 from the left. So here's 2. We're approaching it, coming up here. That's a y value of 2, not 1. I don't know why I said 1. It's approaching 2. As we come into this from the right, again, the y values are getting closer and closer to a y value of 2. And therefore, the limit as x approaches 2, we check these. Are they the same answer? Yes, we're getting 2. So far, everything's looking good. But we're going to run into a little problem here. Because at 2, the function's value at 2 is undefined. So I don't have a solid dot there. So this is undefined. Undefined. Sorry, I misspelled that there. Undefined. And so is it continuous at 2? Well, we need the limit as x approaches 2 to be equal to f of 2 in order for this to work. So this is the question, is this true? Well, this limit, right, is this, and that's 2. So the left side of this is 2. The question is that equal to the function's value at 2? No, because the right side, f of 2, is undefined. I'm just going to put UND. So therefore, they're not equal. Therefore, it's not continuous. And again, you can see, the answer is no again, but I forgot to erase that earlier. The answer is no, but you can see it's not continuous because if I was drawing this function as I got closer to 2, I'd have to pick up my pencil, right, and then continue because there's a hole there. So I guess one of the natural questions would be, is there a place on this function that is continuous? And there's a bunch of places where it's continuous. It's just any place where I don't have to pick up my pencil. So like for example, this point right here at -1. If I were to approach -1 from the left and from the right, if I come in from the left, it's approaching a y value of 0. From the right, it's approaching 0. So I would get, 0 if I'm approaching, this is not one of the problems, but I'm just showing you. If we approach -1, -1, -1, from the left, from the right, it's 0, 0. That means the limit is 0. And then at 0, if we plug 0 into the function, we have a dot there at 0. So this would be 0. And notice that the function's value at 0 is equal to the limit. These are both equal to 0. So it'd be yes, it'd be continuous. And we could do that for any point where there's not either like a break in the graph, a jump, or anywhere there's not a hole. All right, let's look at G, the next problems, which are 27 and 30. So let me list out all the questions first. So for 27, part A, we are asked the limit as G approaches -3 from the left, or x approaches -3 from the left on the function G. Then for part B, the limit as x approaches -3 from the right of this function G. And then 27C, we're asked the limit as x approaches -3, this time from both the left and the right. Then we're asked what is G of -3. And then finally, 27E, we're asked, is G continuous at x equals -3? So all the same sort of questions that we had before. So let's go over here. What is it, 3? Did I draw this right? Oh, -3, sorry. We're going -3. 1, 2, 3. So we're looking at -3 here. And we're approaching from the left first. So as we come in from the left, looks like the y value is getting closer to 1, right? That's 1. So we're going to be approaching 1 from the left. Now from the right, same thing. It's doing some stuff over here, but as we get closer to -3, the y values are again 1 unit high, so we get 1 again. These match, so this is also 1. Now G of -3, we plug in -3, it spits out this point up here. So it's 1, 2, 3. Looks like it's spitting out 3. All right, so is it continuous at -3? No. Why not? Because the function's value at -3 is not matching the limit. These need to match, okay, in order for this to be continuous. And again, you can see you'd have to pick up your pencil, put the dot, and then continue drawing. So no go there. Number 30, we're going to do everything again, but at 4. At 4? 1, 2, 3, 4. Yeah, 4. My picture's not very good here. 1, 2, 3. In between, wait a minute. 1, 2, 3. In between 3 and 4. 1, 2, 3. Yeah, okay, that's actually not bad. Okay. So if we look at this entire picture, again, but we look at what's happening at 4. 1, 2, 3. And my picture's not good. At 4. At 4, you have to look at your graph. At 4, it looks like we're right there at 1, okay? So that's what's happening at 4 there, just so we know what's going on. So we're going to be going 4 from the left, 4 from the right, and then 4, and then we're going to ask ourselves, what's g of 4, and is it continuous at 4? Okay, so from the left, we're approaching x is 4. From the left, we're moving along the curve, and we're headed towards that y value of 1. So that's 1. From the right, we're moving along, and again, we're approaching a y value of 1. Since these match, this is equal to 1. Now, go plug 4 into the function. 1, 2, 3, 4. Plug it in, it spits out that point right there, which is 1, which is nice. Is it continuous at 4? Yes, finally we have one. Why is it continuous at 4? Because the function's value at 4, 1, which is 1, is equal to the limit. Those two are the same, and therefore it is continuous at 4. Okay, that's the first 4 problems. Now let's take a look at number 69. This one's a little different. We're going to be asking similar questions, but we have to actually come up with the graph. So they're going to give us the function, f of x, this is number 69, f of x equals 2 different curves. It's 1 plus x as long as x is less than 1, and it's going to be 5 minus x so long as x is greater than or equal to 1. So here's how I'm going to do this. Draw it first. Okay, so what I'm going to do here is just kind of rearrange this. Keep in mind that this one right here is really x plus 1, and this one is really negative x plus 5. And both of these look like if this was y, it would look like y equals mx plus b. In other words, these are lines. That's a line, that's a line. So if I wanted to do a quick sketch of these, and I should have done this in color, we'll make this line up here the red. I'm not going to make it red if this red doesn't work. I'll make, let's see if this red works. Make this one red, okay? And I'll make that one blue. Okay, so let's do the blue one first. X plus 1 has a y-intercept of 1 and a slope also of 1. So if I were to draw this over here, I'd have a y-intercept of 1, draw a dot, and then I'd have a slope of 1, which means I'd go up 1 over 1. I'd draw another dot, and then I'd connect these with a straight line. Now I'm going to just dash it because of what's coming next. Let's hold off on that. Let's graph this one. This one has a y-intercept of 5. So 1, 2, 3, 4, here's 5. So I put a dot. And then it has a slope of negative 1. So to get to another point, I'm going to go down 1 over 1. And then I would connect those, like this. Okay, now, our graph, our blue graph, only exists when x is smaller than 1. So if we go to an x value of 1, which is here, I can only draw my blue graph to the left of 1. So I need to come and erase this part here. And since there's not an equal sign under there, at this point right here, I'm going to leave that as an open hole. And then let me just draw the line. I'll make it solid now. The dotted line was just to give me an idea where it was. And then when I draw the red one, I can only draw the red one if x is bigger than or equal to 1, which means I can only draw the red one to the right of 1. And so at 1, I'm up here. I'm going to put that as a solid dot. I'm going to erase everything to the left of this. I put it as a solid dot because there's an equal sign here. And then from here, I'm going to move this down like that. So piecewise function, you've got, it's a certain line up to a certain point, and then it switches over to a different one. Okay, let's get to the questions. It says graph it, which we did, locate all the points of discontinuity, and discuss the behavior at these points. So remember, anywhere you have discontinuity is where you have to, like, you have a break in the graph, either a hole or some sort of jump or something. And you can see here that if I start drawing this graph, everything's good. I don't have to pick up my pencil until I get here. Then I have to pick it up and then move. So something is happening at 1. I have a discontinuity at x equals 1. Now they want us to discuss what's happening there. So let me just talk about it in terms of limits. The limit as x approaches 1 from the left, so I'm coming in this way, looks like my y-coordinate is approaching 2. So this function is called f, right? This is 2. However, the limit as x approaches 1 from the right, so I come in this way, it's approaching, what, 3, 4? It looks like 4 here. And therefore, these two limits are not the same, right? So the limit as x approaches 1 of this function does not exist. Even more, f of 1, which is what you get when you plug 1 into the function, spits out 4. So for continuity to happen, we would need this to match up with this, and that's not happening. 4 does not exist, so we have our discontinuity. We knew it by looking, because we had a jump. However, this explains why we don't have it. Okay, let's look at 71. 71, the difference in the problem is that they changed this right here. They changed that to they go less than or equal to 2 here, and then greater than 2. So they use the same functions, okay, the same functions. They just change where the change is occurring. So that does make a difference in my graph. So let me come back over here. I'm going to erase the hole in this part, and I'm going to come back in here, and I'm going to make these dotted again, so I don't have to redo this whole thing. This was the graph, and then this one here was dotted like this, and then here's 2. Okay, now if you were to graph this on graph paper, you would be able to see that at 2 is where these two things meet, okay? Now, I don't have graph paper up here, so it's a little harder, but if you were to do it on graph paper, you would see that everything lines up. So we know that these two lines intersect here. Now, I'm going to draw the blue one to the left of 2 this time. So here's 2 to the left of 2, so I want to make this solid. And I want the dot there because the equals there, I want this dot to be included. And then the blue part over here can be erased. Then for the red one, I want to be to the right of 2, so this side. So I'm going to make that solid over here. And I'm going to erase this part. And I'm going to notice that because there's no equal sign here, I would have had an open circle here. But the blue graph fills in that circle. So when we look at this and we're saying, all right, can we draw this without picking up our pencil? We see that we can draw up here, and then once we get to this point, we actually have a dot here, so we don't have to pick up our pencil, and then we just keep drawing down here. So there is no discontinuity for this function at 2. Everything is good. The function is continuous everywhere. So the answer to 71 is that there are no points of discontinuity. This function is continuous everywhere it's defined. All right, now the last one, we're going to have a 3-piece function. So this is going to take me just a second to draw. My camera is recording, right? Okay. That hasn't happened very often where I forget that, but it has happened before. All right, negative x, 1, and x. And this is going to be if x is less than 0. This will be if x is 0. And this will be if x is greater than 0. All right, so I didn't put if there. It says it in the book. All right, so I have this graph right here is what's happening to the left of 0. This is what's happening at 0. This is what's happening to the right of 0. So I'm going to try and graph this here. I'll use blue and red and green. All right, so this one first. Negative x, that's a line, has a slope of negative 1. So look at this as being, again, mx plus b. Here, there's nothing out here, so b is 0. So I'm going to start at the origin. Slope is going to be negative 1. So from here, it would go like this. Okay, I'm going to do that one first. I'll come back to the others. Or I'll come back and I'll figure out where it's solid and all that stuff. This right here, 1, is only happening when x is 0. So this is actually telling you at 0, your function's value is 1. So at 0, I'm up 1. That's all that tells you. Then the last part, we need to be this function, which again looks like this. Slope is 1, and there's y-intercept of 0. So I start here at 0, up 1 over 1, up 1 over 1, and so we have this line. That. And now let me come in here and make things solid and erase some stuff. This blue one is only supposed to happen to the left of 0. So here's 0 to the left of 0. I draw like this. And I will put an open circle here. Erase this. Open circle because there was no equal sign here. We already have the green dot up there. And now the red one is to the right of 0. So that's this way. This. And then open circle at 0 because there's no equal sign here. And then erase this. So there's my graph. If I try and draw it without picking up my pencil, I'll come down and then up. I've got to pick up my pencil, draw the dot, and then come back down and continue. So there's something happening here at an x value of 0. And so let's talk about the limits. The limit as x approaches 0, I'm not going to do from the left or right because I think you hopefully understand this by now. Can you see here that from the left we're headed towards 0? And from the right, we're headed towards 0. So that means both sides we're headed to the same place, a y value of 0. So this is 0. Okay? Now we're supposed to check to see if that matches the function's value at 0. Well, the function's value at 0 we were 1. And for it to be continuous at 0, we would need these two to match, which they don't. So therefore, this is discontinuous at x equals 0. Everywhere else, the function is continuous because we're drawing without picking up our pencil. So we only have 1 point of discontinuity. All right, well, that's it for the homework.